I have defined potential energy, and of course, I have alluded to that there are many more. But I know the process of discovering potential energies. I simply observe a force and see if it meets my two criteria. One is that it should only depend on position, and that the work it does should be independent of path. And then I can simply apply the work-energy theorem in order to calculate that work, and that work is then the potential energy. The potential energy depends only on the configuration of the system, that is the location of objects, initial and final, and that's how that works. So I have two potential energies that I've defined. So what I want to do today is go back to the work-energy theorem and do a little bit more analysis in the light of realizing now these different kinds of energies that I have in a system. So I'll start with the work-energy theorem. The work, naturally, is equal to the change in the kinetic energy. See, I've already started to make a mistake there. I was writing the last equation instead of the first equation. The work done is equal to the change in kinetic energy. But now I know that the work done by forces can be divided into two classes. Work done by non-conservative forces and work done by conservative forces. Non-conservative forces are forces like friction and viscous drag, and the force of somebody pushing, the inner nature of the force I'm completely unaware of. If a person is pushing on a piano or something, move it along, then the work that they do depends on the configuration of their body, how fit they are, what they had for breakfast. It's certainly not conservative. There are so many conservative forces, or non-conservative forces, but a limited number of conservative forces. So on this side, on the left-hand side of my expression, I'll divide the work into two. I'll say the work done by non-conservative forces plus work done by conservative forces, and that W sub C, that's very temporary. I don't like that notation in particular, but just showing that I have two kinds of work being done is equal to the change in the kinetic energy. But now I appreciate that the work done by conservative forces is equal to the negative of the change in the potential energy. So replacing that in this expression, the work done, minus the change in any potential energy. And when I write the potential energy there, we should appreciate that there are, in our physics, for the moment, two kinds of potential energy for right now. They are the gravitational potential energy and the spring energy that we expect to see in our problems. So that's the change in all forms of potential energy. Well, I got a minus sign here. And so I'm inclined to add the change in potential energy to the other side of the equation so that the work done is now equal to not only the change in kinetic energy, but also the change in the potential energy. See, so in a way, I changed my thinking to imagine that conservative forces have associated with them potential energy. And the action of conservative forces on the system is no longer work. It is itself energy. So I've taken all the conservative work and shifted it over to the right side of the equation and christened it potential energy. So on the left side, I have work done by all non-conservative forces, work done on the system. And my philosophy is that what work does to a physical system is it changes the energy. But there are two kinds of energy, kinetic energy and potential energy. So I am inclined to write an expression that we're all already generally aware of, that the energy, which I give the symbol capital E, of a mechanical system is the sum of two kinds of energy. The kinetic energy that it possesses plus the potential energy that it possesses. This is generally referred to as the total mechanical energy of the system. The total mechanical energy, the sum of all the kinds of energy that it can have. And so now, with that in mind, I can write the work-energy theorem in a new form. And as it turns out, according to me, a more practical form. And that is that the work done is equal to the change in the energy. It's important for you to be thinking about these deeper than just the equations, because look what I've done. My original version of the work-energy theorem, which I sometimes refer to as the generalized work-energy theorem, is that the work done is equal to the change in kinetic energy. Now I've said that the work done is equal to the change in the energy. It's like I've changed the expression, but you realize that I haven't. Because in the original version, it was all work. And here on the left-hand side, it's non-conservative work, because conservative work has been shifted to the right-hand side and becomes part of the way that I think about energy. So now my philosophy, changing a little bit, is that when work is done on a system, the energy of the system increases or decreases. And that increase or decrease in the energy will manifest as changes in kinetic energy or changes in potential energy. That's how I see things. Now, I'm going to take this idea and make a very, very practical statement out of it, which is how it's going to express how I want you to approach every energy problem that you solve. It's not just an equation, but a philosophy, a way of thinking. And I find, as I teach physics on all varying levels, that it's difficult to convince students to buy into this, but it's very, very critical that you do so, because everything that happens in the universe, everything that ever happened or ever will in the universe, follows this law. In a way, it's the most important law that you will discover in any of your technical instruction. So here I go. If the work done by non-conservative forces is equal to the change in the energy, then the work done is obviously equal to the final energy minus the initial energy of the system. The final energy of the system is calculated by looking at the system in its final state and observing all the different types of energy that you know of. In our case, that is kinetic energy. Kinetic energy, easy to spot. Kinetic energy, the energy of motion. If it has a velocity, then it has some kinetic energy that I can calculate. And if I look around and see that there's a spring and the spring is stretched or compressed, there'll be some spring potential energy. If I find that it has a position in my coordinate system above where I've chosen 0, then I have some gravitational potential energy. And it's a number that I can calculate, the total mechanical energy in the final state of the system. Similarly, the initial energy of the system, I look at the thing before it's transformed. And I can write down the kinetic energy, gravitational potential energy, and spring energy, and in the future any other potential energies that exist, and add them all together. You should have the feeling right now that this goes exactly to what I said right at the beginning of our discussion of energy, that energy is a number that you can calculate. Well, now the number is more sophisticated than just calculating kinetic energy, but the other energies as well. But it's quite simple, isn't it? I simply add up all of the energy that happens to be laying around at a given instant in time, and I add it together. The initial energy and the final energy, and here is the change in the energy, obviously. So what I'm going to do is add the initial energy to the other side and get an equation that you may not find emphasized in a lot of textbooks, because this is just sort of the way that I have come to think about problems involving energy over the course of a very long career. Now with the initial energy moved over to the left-hand side of the equation, this equation reads that however much energy the system has, plus or minus the non-conservative work. Now the plus or minus has just spontaneously appeared in my expression here. What do I imply by that? The work that's done on a system, non-conservative work done on a system, like the work that a man does pushing a piano, that non-conservative work can have two effects on the total energy of the system. It could increase it, or it could decrease it. And so I've written a plus or minus that implies to me as a concept that the work done on a system could increase or decrease the total energy of the system. If the total energy of the system decreases, that means that the energy of everything outside of the system is decreased. Or, sorry, I said it back the same way. I'll start again. If the energy of the system decreases, then the energy of the environment has increased. If the energy of the system increases, then that means the energy of the environment has. A funny thing is, if you go on to learn engineering thermodynamics, they reverse the signs on that. As a concept, they reverse the signs. It's a lot of fun. It gets confusing for the physicists to try to do engineering when they reverse the thermodynamic signs on things. Well, there you go. So the work can increase or decrease the energy, and then what do I have left over? I have the final energy of the system. This is how I should think about every problem that I solve. I read a problem description and it tells me some crazy nonsense is going to happen that involves springs and things shooting up in the air and moving with velocities here, there, and everywhere. I look at the initial state of the system and calculate or write an algebraic expression that represents the initial total energy. And then I write an expression or a calculation of the work that is done on that system during the process that is being described. And then I write an equal sign, and then I do the calculation or write an expression that expresses the energy at the end. That is how all problems involving energy are solved. All problems are solved that way. Now, I emphasize this because there's all kinds of bizarre problems. All kinds of nonsense happens. And from the student point of view, it may look like, well, now maybe I have to do something different because I've encountered a problem the likes of which I haven't seen before, a problem that looks sophisticated or complicated, a lot of elaborate things happen. It does not change the fact that this law is what's at play. There may be some disagreement in textbooks or whatever as to what I'm saying here with this law. I refer to this as the law of conservation of energy. And the reason why is if a physical system is isolated from any non-conservative work, that is, if there's no friction or viscous drag, and there are no external actors on the system, like human beings pushing on it or other external influences that can do work. If no non-conservative work is done, then I run into a situation where the work done here, in my expression, is equal to 0. So I'll just write it again. The initial energy plus or minus the work is equal to the final energy. But if I strike out that non-conservative work, if I eliminate non-conservative work, from my system, then the energy is conserved and the initial energy is equal to the final energy. That is the law of conservation of energy. Now, it'd be a really brilliant thing right now if in your head you had a little suspicion and you said, wait a second, isn't there friction in everything? Is there not viscous drag in everything? Is it not impossible for me to account for every non-conservative force acting in every given situation? You're absolutely correct. So very often when we make practical application of the law of conservation of energy, when we make a practical application of it, we're doing it in approximation. Sometimes that approximation is excellent and we can get good and useful answers using the conservation of energy in an approximate way. But it's really important, a subtle thing about the universe that I want to make clear is that the law of conservation of energy is not an approximate law. The limitation of the law of conservation of energy and approximation is our system, what I choose to be the system. For example, is energy conserved on the Earth at large? Because imagine here in the lab, I do an experiment and I have a block that skids to a stop, which you're very familiar with. This is essential that I can solve. And a block skids to a stop. It has kinetic energy, and then it doesn't. There's no change in gravitational potential energy. There are no springs. So it had kinetic energy, and now it doesn't. Where did the energy go? Well, I would discover under close investigation that when the two surfaces rub together, thermal energy is produced between the two. The surface of the table gets hot. The block that's skidding to a stop gets hot. That thermal energy is transferred to the air in the room and goes out the window. So it is in my accounting for the energy that I lose it. Imagine instead if I could keep track of all of that thermal energy. If I could keep track of all of that thermal energy, then the energy would ultimately be conserved. Well, it's very difficult to keep track of thermal energy. The specific heat of the table, the mass of the table, how the energy distributes itself. The air comes by, it gets to the air, and the air, gradient temperature of the air in the room, and indeed the air goes out the window. It's very difficult to keep track of that. So the energy is not conserved. You say, yes, but imagine if we could take the entire Earth and consider that to be our system. Would the energy be conserved? Not even close. Because? Not even close, like wildly not conserved. Why? In particular, sunlight. Sunlight. The chemical potential energy in your breakfast this morning that you're taking advantage of simply to be awake ultimately was energy created or released in a fusion reaction inside the sun. And that sunlight came to the earth and the plants grew and then they were cultivated and made into cereal, which you then shoveled into your face this morning and then therefore. So I draw a bubble around the solar system. Is the energy conserved? Yeah, there's all the stars outside, but it's closer, isn't it? A lot closer. Because the energy of the starlight that comes out and the gamma radiation and whatnot that comes cosmically into our solar system is actually much lower, right? So it's even better. What if to take the universe as a whole, is the energy ultimately conserved? Get busy trying to answer that question. Now, so you say, well, the conservation of energy there, I have to be very careful how I apply it. Now, if I go to interactions on a subatomic scale, is the energy conserved? In a lot of cases, absolutely, because I can count the number of photons that go out and the interactions between particles. So I can have systems that are small enough, that the details are small enough, where the law of conservation of energy applies absolutely. My point is this. The law of conservation is absolutely true, so far as we could tell, possibly. And I think it's true that it will never be shown that it's not. But you have to be careful how you apply it. And so the successful application of the law of conservation of energy, for me, lives in this notion. Calculating the initial energy, appreciating work that is done to increase or decrease that energy, and then writing the final energy. If I can write that expression, that is how I solve problems.
What other W would you use? Obviously, you wouldn't plug in E minus E naught for W. What other value?
If you don't know the work that is done, then you've got a serious problem in terms of solving, right? It comes down to the same thing that all problem solution does. There's knowns and unknowns. And the conservation of energy is but one equation. If it has more than one unknown in it, I'm in serious trouble for solving, right? That comes down to a strategy for how I solve problems successfully. And we just recently had the problem with the push rod and the wedge goes under. And I was trying to assert very clearly that I do my Newton's law stuff and I have too many unknowns. So I have to write more equations. So you're implying that, well, what if there's lots of stuff that I don't know? Well, then the law of conservation of energy is not really going to help me. I need to bring in other physics, hopefully, in order to leverage the solution to a problem. Steve?
It's all about non-conservative forces.
Right.
How you were talking about spring energy. I thought that was
Right. So what I'm saying is I want you to change your thinking. Instead of thinking about spring force, I want you to ignore the spring force completely and always consider it to be spring energy. Remember that I said that my strategy will be to always solve problems from the point of view of energy, whenever possible. Now, Blake imagines he's very correct that there would be situations where I have to bring in other physics to solve problems. It's totally true. But whenever possible, I should start from scratch with energy, and I should always think of springs as spring energy and not calculate their work. Because you know a thing that's true. If you calculate the work done by a spring, force, in every problem that you solve, you know what you're going to get? 1/2 kx squared every damn time you do it. So at some point you got to go, well, I should stop doing that. I get the same result every time. And call it energy instead of calling it the work done by a spring. Think of it as energy. So that's sort of the philosophical change that we're making there in terms of problem solving. Yeah, I like it.
So that was the final.
Nope.
Is that it?
Some who have studied physics before might feel that this is everything that I've done here is very familiar. I'm about to do something that none of you have seen before because it's bringing a calculus aspect. Well, I've already brought in a calculus aspect because I have written for you that the work done is, by definition, my most general definition, is equal to the force vector dotted into the displacement vector, so the integral of f dot dr. So that's where the calculus came in. That's the unfamiliar part for those of us who have seen some physics before. But now I want to investigate that in the context of the potential energy. Because recall that what I'm saying is that in the case of work done by conservative forces, that the work done is equal to the negative of the change of the potential energy. So now I can write an expression that says that the change in potential energy, delta U, is equal to the negative of the integral of f dot dr. And now I get to take advantage of some of the way that in the introductory lectures I talked about calculus. Because I have expressed before is what happens when I add up all the little changes. I get the whole change. So what this integral of the work must be is adding up all of the little changes in potential energy that take place. Which means on the left side of the expression, watch this, I'm going to sort of do calculus in reverse. If this integral is equal to the whole change in potential energy, then a differential change in potential energy, du, must then be equal to the negative of the force dotted into dr. And so I get an interesting relationship between conservative forces and their potential energies. A relationship that I might have guessed at, but that a conservative force, or that I should say, I'm going to take the vectorness away from it now. I'm going to remove the vectorness and say that the magnitude of a conservative force, I'm not going to put magnitudes on my F, I'm just going to leave the harpoon off, all right, so you appreciate it. The magnitude of a conservative force is the negative of the derivative of the potential energy with respect to r. So if I happen to know the potential energy is a function of position, and of course potential energies being derived from conservative forces are explicitly functions of position. So if I know that potential energy is a function of position, then the derivative of that potential energy with respect to position is in fact the force. A really obvious case of this that I'll write as an aside here, just like a little example, is that the potential energy as a function of x might very well be 1/2 k x squared. That could very well be the potential energy as a function of x, and you recognize it. It is the spring potential energy. If I take the derivative of the spring potential energy with respect to x, I get a rather obvious result. 2 comes down, cancels, negative sign appears. The derivative. I leave the negative sign off there for the moment. Is k times x. When I take the derivative of the potential energy, I get the spring force. Naturally, quite naturally. When I take the derivative of the potential energy, I get the spring force back again. And the force is the negative derivative of the potential, and so the spring force I find is equal to negative kx, exactly as I expect. And this is true for more sophisticated potential energies, and you will, as a practical matter, as a student, find yourself taking the derivative of potential energies as a function of position in order to discover what the force would be. The caution for that is students often get burned, particularly on multiple choice exams, forgetting about the negative sign when they take the derivative, right? To think about that negative sign, I'm going to show what this potential energy looks like graphically. What does the potential energy of a spring look like if I should make a graph of the potential energy, U, as a function of x, the position? Well, naturally, it's 1/2 k x squared, so it is a parabola. And when x is equal to 0, it's 0. Difficult to draw. Oh, I did pretty well. That parabola is a potential energy as a function of position, but you know darn well I don't like the way this x-axis looks. Oh, now I do this to myself sometimes. It's a sad thing. Oh, well, that's it. Imagine, if this is the potential energy, how shall I interpret the derivative? Well, the derivative of the potential energy is the slope. Imagine I look over here at a position here, along the positive x-axis, arbitrarily chosen position. What is the slope at that point? Well, I can draw it. It's tricky to draw, but that slope is drawn through that point right there. difficult to draw on a diagram, but that slope is drawn through the point. Notice it's a positive slope. So I take the derivative, calculate that slope, and the slope is positive. The force, however, is restorative, and the force is directed back toward 0, which is the equilibrium. So the force pushes back toward the equilibrium position. The force pushes back toward the equilibrium position. Look over here. For negative values of x, the slope is negative. But according to my relationship between conservative forces and their potential energies, if the slope is negative, then the force is positive. So then this relationship shows me quite explicitly the restorative nature of the spring force, always driving the system back to the equilibrium position, which at the very end of this first half of our physics course, that's going to come to spectacular effect. A word of warning for you here in the immediate audience, that on our exam for this material, I fully intend to give you a potential energy, the likes of which you've never seen before, and ask you to interpret the force from it. So you should pay careful attention to this sort of idea. The relationship between potential energy and force, I'm not calling it an essential for our course, but I guess I'm calling it very, very important. To finish up and round off the material we study here, I have one more thing to talk about, and that is the rate at which energy changes, because I understand that in any given physical system, the total mechanical energy that I've defined could change. It could increase or decrease because of the work that is done. Now, that work might be done rapidly, or it might be done quite slowly. And so there is some interest in knowing the rate at which the energy changes. But I could also focus on my system and simply examine the kinetic energy of it and realize that because the velocity changes, the kinetic energy might change. And the rate at which the kinetic energy changes is of some interest to me. So there is a whole family of rates of change that I'm interested in that are obviously related to the rate of change of the energy with respect to time, dE dt. dE dt has a name that we're very familiar with. It's an extraordinarily colloquial name. The derivative of the energy with respect to time, naturally you all know, is known as power. Not power in the colloquial sense, like political power, although power means, the ability to affect change. If you cannot affect change, you are powerless. But power in the scientific sense, the rate of change of energy. Now here comes a Scheidleism, a thing that only I do. No one else does it. The symbol for power is an uppercase cursive P. And I don't have an uppercase cursive P that I'm happy with. I just don't have one. And so for my whole life, since I was a wee child and first picked up a crayon, I have been writing power as a backwards paragraph symbol. So it's like a P with, that's a bad version of it. If I'm going to write it for the first time, I have to write a good version of it. It's a P, but it has two legs to it. And it's really important that I have a unique power symbol. It's really important that I have that. Because later on, you take a course in engineering thermodynamics, and I'm your professor, and late in the course, it's actually quite fun. We're talking about how to design power plants. So we need a 10 megawatt power plant that we're building. It has a steam turbine in it, a boiler and a condenser and all these things. And we're doing that. I have to express the pressure, which is capital P, in expressions where I also express the power, which is capital P. So I need to be able to distinguish those symbols, which is why I'm going to obsessively write the power as P. So here's this relationship. It's equal to the rate of change of the energy, and I just simply want to reestablish, make very, very clear, any kind of energy. I can calculate power in the context of energy, total mechanical energy. I can calculate in the context of kinetic energy, potential energy. I can calculate it in the context of work. It's not really a good thing for me to be writing here, but I can also define power as the derivative of the work with respect to time. By putting, I'm going to put arrows because I don't want to write equalities because they're not equal to each other, but they're just different ways of expressing the power in the context of a problem that I might be solving. So I can do it all these different ways. The rate of change of energy is an interesting quantity. And so there are all these different ways to calculate it. But here's a critical one, a critical way of calculating, or a calculation that you've never done before, that you'll probably be called upon to do. If the power, we're just rewriting the law here, if the power is equal to the derivative of the energy with respect to time, as I write here, I can rearrange this to write that the differential of energy, obviously, is equal to the power dt, which begs an integral. So I'll integrate both sides of the equation, and when I do, integrating dE obviously gets me the whole change in E. is equal to the integral of power dt. You might find yourselves in the future in situations where you do not want to perform that integral because it's quite complicated. However, you can't deny the utility of it. If I have a certain power, and that power changes as a function of time, the integral is the only way for me to answer the question, how much energy? For example, if I drop an object from rest and it falls under the influence of gravity and viscous drag, if I'm asking the question, how much energy is lost, then I can calculate the change in kinetic energy. But if I'm asking how much energy is lost as a function of time, I'll have to perform this integral to find. And so this is a useful thing to have around because I could have the power as a function of time and be asked the question, how much energy? And that's how that goes because of the definition of power as the rate of change of the energy.